Hello friends, let's have a look at the Everything Everywhere AA once. Okay, so I got this title from a recent movie called the Everything Everywhere All at Once, and got this idea of making a legendary series with this title. So without further ado, let's get started. Okay, so 2022, I think for me is a great year for cinema, right? Because of this great movie called Everything Everywhere All at Once. If you haven't watched it, it's a great film from A24. This is one of their masterpieces, so please to check it out. And another movie called Nope has been also a wonder, right, for the movie. And every time I see those like a great inspiration, I get the idea of making the video for the for the IID service. So let's try to combine them. Okay, so what I like to do is to change the title from the All at Once as the AA, right, analysis and approaches, and see what we can do, right? So what I like to do is to combine our collective understanding from topic 1 to 5 to solve this following problem of the Bernoulli number with the zeta function. So that is what we are trying to do, right? So this is a big idea, right? So this is the representation for the zeta function of the even term. So if I quickly give you the idea of what the zeta function is that z of 2k is represented by the series of the harmonic series of the, what is it, n to the power of 2k. So it's going to be of, what is it, 1 over 1 to the power of 2 plus 2k, sorry, 1 over 2 to the power of 2k, goes on and on and on. And it's an infinite series of the index n1 to infinity. And then we would like to know what the convergence is going to be, described by the Bernoulli constant, Bernoulli coefficient, Bernoulli numbers. And this question captures everything what we learn in school, for the IB, especially for the AA syllabus, and let's try to discuss with that, okay? So what I like to do is this, to remind you what we need from the topics to tackle that problem. So topic 1 is what? We need the understanding from the sequence and series and binomial expansion and a bit of complex numbers. And then we are also going to talk about the function in general, polynomials, and graphing using the calculator. And topic 3, yes, mainly we're gonna need trigonometry to solve it. Unfortunately, I wouldn't have many vector techniques to solve this, but later on in the another series, I like to tackle maybe some of the zeta function with just a vector, right? So please stay tuned. And topic 5, yes, I want you to notice that I skipped a bit of the topic 4 because that's the later part. But topic 5, yes, everything of a calculus we're gonna apply for this problem with the Bernoulli number with the zeta function. And yes, I like to talk about topic 4 relation with this question, and that's really thoroughly goes over what we are going to learn with the contents. Okay, so without further ado, let's get started. So for the topic 1, it's really the study of a discrete and complex number, hence called the algebra. And I like to start with a scene from the movie called the Everything Everywhere All at Once. Again, let me emphasize, one of the greatest movies I ever seen in the cinema, so please, if you haven't, check it out, okay? But yes, that inspiration plays the role of our initial question here. So let's start with the power sum. So yes, I know it's not in the syllabus, but it is a very, very popular for paper 3, okay? So it's a very, very popular for paper 3 exam question. And you can easily derive it using the binomial expansion and the series, okay? So I really want you to be able to memorize the terms as well as being able to prove it. And you know, who has been the most popular form to actually appear in the exam or textbook? Yes, the second one is one of the most popular form to expand, okay? And if I quickly show you how to derive it, is that what we like to do is to start with the cubic expansion, right? Let's go with this binomial expansion. As you can see, one of the major things from the topic 1. If I use the binomial expansion here, we can expand it, and what I like to do is to rearrange. You see, so I'm going to rearrange this to the other side and then the rest. So I just shift it around, so now I see the difference of cubes, okay? So that is great. On the right-hand side, I got this left over of the quadratic term. That's great. So what I like to do is to take the sigma. I'm going to take the summation on both sides to talk about the sum, okay? And then what you actually get to enjoy, one of these method to derive those power sum formula is to work with something called the telescopic cancellation, okay? So this is very examinable for paper 3, so I want you to always practice with this series. And then on the left-hand side, I'm gonna perform the telescopic cancellation, okay? So that is great. So if you did, so I will leave it as an exercise for you. It's not that bad. It's not that hard, actually. If you just start plugging from k equal to 1 to n, and then you see whole part of the series actually cancels out, only leaving the second and the second last term, resulting just the n cubic. So that's the leftover of the telescopic cancellation. But on the right hand side, I like to use the linearity of the sigma. So that means I'm going to take the sigma on these three terms, which I just managed to do so. And this is the aim, isn't it? This is the aim, right? And then what we do know is by the property of sigma, if you just add the constant n many times, that just becomes n. And sum of integers, by using the arithmetic series formula, you know that it must be n times n plus 1 over 2. So if I just substitute in, and my aim is the sum of k squared, you can just rearrange everything to derive this following result. You know, it's a very, very standard result, and you should know how to prove it because it could be potentially the one part of your paper 3, and use it for, you know, Riemann sum or deriving the volume formula, etc., etc. So please get to know this. You know, this is gonna be popular. But yeah, you know, that's how you derive it. Then obviously we want to generalize the formula, right? So if we go of the sum of rth power till the n minus 1 term as the following sum, you know, this is how we're gonna define this power sum form, right? So what it says is that I'm gonna raise the power of r up to n many terms. Sorry, n minus 1 many terms. That's what we are defining here, right? So it's, as you can see, from 1 to the power of r, 2 to the power of r, I'm going all the way up to who? N minus 1 many term to the power of r. And that is how we are going to define it. Okay, so that is a great. So then, you know, what you can do is actually you can derive it using this sort of a difference equation here that will result just to n to the power of r, right? Because n plus 1 goes up to the n term, and if you subtract, only the last term is going to remain because the first r many term, so first n minus 1 many term we cancel out, isn't it? So I've got this n to the power of r, and then with the initial condition that the 0 is going to be 0. Okay, so this is how we generalize it, right? And in fact, what you can actually derive is the other terms, right? So, you know, what we have done was sum of integers, integer square, and integer cubic, but then, you know, if I put it as n, that means I'm going only up to n minus 1 many term. So what we just did is just to substitute with the n minus 1. So this is a little extension, but it's fine. You know, we can just substitute with the n minus 1, and using the formula, you can actually derive up to 4, 5, 6, 7, etc., etc. But not only have I done that, what I've done is just expand it, right? So I just expanded and put it in a descending form, right? That means starting from the highest degree, highest power, and it goes to the constant, right? But now we have up to linear term. So that is great. So that goes up to power 4. Okay, so why don't we try to sort of display this more visually? Maybe try to use a symmetry. So what I mean by that is, you know, for this term, maybe I would sort of try to put this in a lower triangular form. Okay, let's see what we can do. So if I try to go up the power form of power 1, 2, 3, or go all the way to 6, and then put it into sort of this diagonal way, now I want you to see what sort of a pattern you get for the coefficient of each term. Okay, so if I just see vertically, right, from their highest power, I see 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. Okay, I see the pattern. All right, what about the next term? So then it goes with negative 1 over 2. All right, that is great. I see the pattern there. But then the pattern sort of stops. All right, the pattern sort of stops, and then starting from the third one, right? Because I don't see any pattern there. I don't see any pattern there. So that is almost patternable, but it's not, right? But what we like to do is, for 1, I'm going to factorize everything by 1 over 2. For 2, I'm going to factorize everything by 1 over 3. So if I had a SR of n, I'm going to actually factorize everything by 1 over r plus 1. And let's see what we get. Okay, so there wasn't much of a pattern for the remaining terms, but now if I factorize everything by 1 over r plus 1, for which I just did it for you, you can now see the coefficient actually does have a pattern for the remaining terms as well, with the binomial coefficient of what? N choose 0, n choose 1, n choose 2, goes all the way up to n choose n minus 1. That is great. So I see those patterns which you actually remember from the Pascal's triangle. And not only that, the leftover coefficient. So what I've just done now was to factorize by 1 over r plus 1, and I'm using the binomial coefficient. And then the remaining parts of each term does create a pattern, right? So if you check it out, what we had here was just a 1, and I got negative half. Okay, that is great. And then the next one goes with 1, negative half, 1 over 6. That is great. And the next row goes with 1, negative half, 1 over 6. Okay, then where is the another one, right? So it's supposed to give me the term. Why don't we have it? That's a good question. But if I continue, of the next row, I go with 1, negative half, what is it? The 1 over 6 and 1 over 30. And you can see the pattern on and on and on, right? So that's very interesting. That is very interesting. What sort of a pattern are we doing is the main thing of this expansion with the power sum. By factorizing the, 1 over r plus 1, and then using the binomial coefficient. This is the representation of a Pascal's triangle, but my coefficients were not just done by the Pascal's triangle. I still have some numbers that are making some pattern, but I don't have their sequence. But there is a special name for those numbers. There are special names for these fancy coefficient of these numbers after having factorized with 1 over r plus 1 binomial coefficient. They are actually known to be who? So those numbers are actually known to be the Bernoulli's number, okay? And that is one of the main aim that we would like to do to tackle so that we're going to collectively use our understanding from AA syllabus. So now we saw this number using, the sigma notation, power sum, and then binomial expansion and Pascal's triangle, right? Using this, I see this interesting pattern of the numbers and I like to find their sequence. But what we can do is to see the list by using some manual work, and then these are some list of the Bernoulli's numbers starting from the 0th, which is the first, and then negative half, 1 over 6, etc., etc. And now what I want you to sort of notice as time proceed, you notice that starting from the 3 and then all the odd term becoming 0. But would it be just a momentum? Would it be just for this period that becomes a 0? But would it be giving all the odd term being 0? I don't know. That could be a very good IA topic, right? But anyway, so if I use a sigma notation, this is how we're going to represent the power sum, right? So what we saw is that we were factorized by 1 over, well, we set the r plus 1, but let's just try to use for the m. 1 over m plus 1, if you factorize, we saw a bunch of the time represented by the binomial coefficient multiplying some number, remaining numbers. Those remaining numbers represent the Bernoulli number. So I'm going to call that bk. And then it's going to be multiplied by those, the polynomial term, right? So that is great. So that is the appearance of the Bernoulli number from our familiar expressions such as the sigma. Okay, that is great. But obviously, when we define things, you need to prove whether this is really true or not. And what method of proof would you like to do is another discussion, right? Another extension from the topic 1, because topic 1 involves proof by deduction or induction. For such claim, what proving method would you talk about is also a great discussion, great topic for the internal assessment, right? But that is really the start. So this is the appearance of a Bernoulli number from the power sum. And that is what we're going to start with this topic 1, okay? But then now what we would like to do is where else can I see? What other techniques can I use from the other topics to associate those Bernoulli constant and then eventually to link this with the zeta function for the even term is our great aim, okay? So this is just the opener for the problem, but what I wanted to show you is that you get to see these numbers even early on in topic 1 using the summation and Pascal's triangle and binomial coefficient, okay? But yeah, that's pretty much it for the topic 1. Let's move on to topic 2. Hello, let's have a look at the appearance of Bernoulli number in other field, such as a topic 2 function, right? I got this image from the movie called the Everything Everywhere All at Once. It's the lead female character who gets to move around the metaverse and get to play the different role of her life. And that's what really the topic 2 is all about. When you start working with the function, what your main focus is about the polynomial function and transcendental functions, non-polynomial functions such as a sine, trigonometric function, exponential function, logarithmic function. But what I really want you to realize, in fact, they are really connected, right? So that's what this metaverse is all about too. It's all connected. And that's what we're trying to work to. So let me quickly start with this curious case of a sin x over x. I recently made a video about that too, right? But we didn't really dive too much in deeper of the sin x over x with the Bernoulli, with the zeta function, but with the Basel problem. But we can actually talk about that more. So let's have a look at the sin x over x. And we saw that actually in IB exam, we get to see his appearance many times. Paper 1, paper 2, or paper 3. And there's a great reason for him to be so popular because it was one of the functions that Euler used for solving the Basel problem. And let's then put ourselves in his shoes. Okay? So what we want to do is to talk about the metaverse of our function, right? Because what we assume is a sin x over x is got trigonometric function. We think it's a, transcendental function, hence cannot be expressed as a polynomial, right? But here's the thing, of sin x over x with his roots, I'm concerned about just numerator being 0 are integer pi, right? For sin x to be 0, we know it needs to be the integer pi, which I call it k pi, where k is an integer. However, yes, if I put in 0, it's a 0 over 0 indeterminate. We saw it from the function graph, it actually has a limit at 1. So, what I want to do is to exclude that case. So I got those roots. And what we remember from the study of topic 2 with the function and polynomial is that if I know their roots, I can actually factorize with the linear factors. So what I claim is the following. I can say that, okay, my sin x over x must be factorizable with this multiple integer roots, right? And what I notice is that, okay, so if it's integer roots, it's going to be plus minus pi, plus minus 2 pi, etc., etc. And in fact, what I can do is to use the difference of the square to express it, right? So it's going to be x squared minus pi squared, x squared minus 4 pi squared, etc., etc. Well, let's say, the 2 pi perfect square, okay? So what I can do is just express this as a difference of a square. And yes, this is going to be infinite product, and obviously we don't want to write all the product in our hands, so what we do is to introduce this new notation pi, right? The sum is the sigma capital letter of S in Greek alphabet, and P Greek alphabet capital letter pi is used for product, for the multiplication. So that is great. So what I've just done now is to claim, because I know his roots, and from my polynomial chapter understanding, I can actually factorize it with this integer pi. And what I'm claiming is that this function must be described by this polynomial function. Okay, why not? But here's the thing, what sort of a behavior do we expect? Of course, more I multiply, it should actually be, right, converging to the shape of a sin x over x. And let's really check whether that's the case. Okay, let's see from the graph. And what their, asymptotic behavior means, all of their ratio, right, if it's the sin x over x, and that, if I call that as fx, if I call this as a gx, right, so their ratio, right, must converge to 1. Right, so that's what I want to see. That's what it means by this asymptotic behavior. That means eventually they're going to be the same thing, right? So let's see from the graph. So this is the typical shape of the sin x over x. That's very typical. And I want you to memorize the shape because it could potentially be on the paper 3. It'll appear already twice. Okay, so please make sure you know it. Okay, so that's the sin x over x. And do you remember the infinite product, the one that we defined it as a x squared, of the integer pi square? So what I've just done now is starting from 1 to 10, I just describe as of the multiple of the product of 10 terms, and this blue function represents that polynomial. But I want you to realize, as you can see, it doesn't look like the sin x over x function that we wanted to describe. Although they do have the same x-intercept, but the shape doesn't look any come closer. And what we do know is that from their asymptotic behavior, I know their ratio should eventually be 1. But if I look at the picture of their ratio, the fx over the gx, as you can see, it's just completely flat, representing the ratio is in fact 0, meaning that I'm actually dividing a very large number, very large value of a gx. Well, no wonder why, right? Because if you actually look at the polynomial function that we said, this is actually pretty large, especially if you actually look at the constant term, right? Because if you think about the constant term, what we are doing is consecutive integer pi square. Pi, 2 pi square, 3 pi square, 4 pi square, 5 pi square. Those values are actually quite large. And 5 pi square is 25 times, 3.14, and then you're multiplying that on top of that with other integer pi squared. It's a very, very large value. And obviously that constant term is causing a crazy error. So we don't want that, right? So no wonder that it wasn't converging to 1 for their ratio to be asymptotic behavior, right? We don't have that because the gx is so large. One of the main error that we can definitely point out is the constant term because it's so big, it's so large. And what we want to do is to reduce the error. We want to calm him down a little, right? We want to calm him down a little. So that means I really want who's the bad boy? Who's the troublemaker? Yes, the constant term. And then the one way that I can actually calm him down is maybe I will divide the linear factor with the constant term, so that if you divide, eventually you're just multiplying the constant part being 1. Okay, so what I like to do is instead of representing this linear factor, which does have the roots of sine x over x, but it was causing too bigger the size because of a constant term, if you factorize the term by the constant term, preserving the roots, and also the constant term will eventually become 1. Right? No matter how many terms you multiply, you're dividing itself, so it becomes 1. So that is great. So what I slightly suggest is to actually work with the reduced factor by coming up with this factorization. Okay, so now I introduced another gx. This time, yes, the polynomial, but what? More reducing factor by factorizing the constant term after having realized that this constant term was causing the trouble because it was so large. Now let's see the behavior on the graph. So now this red function is the polynomial, right, of the product of the first 10 terms. But as you can see, the green function is the sine function. And as you can see, it's pretty close. That's very, very close. Well, obviously x gets bigger. We see the difference is getting bigger and eventually diverges simply because we only introduced the 10 many terms. But I bet that if you increase the more terms, it's actually going to converge. As you can clearly see this, very accurate approximation for a short period of time, even with the 10 terms. But remember, the product is supposed to be infinite in many terms, and I'm sure that convergence is going to be achieved, and which could be a very good IA topic for you actually to prove that the ratio will eventually be 1. But here's the thing, check this out. What I have suggested was just the 10 terms, but if I go with the first 11 term of 11 terms, as you can see, it got flipped. You see? My function, the red one, the polynomial, now it's reflected, you see? Well, I'm just multiplying with the polynomial term, and then depending on the number of terms, it sort of alternates. That's what they're saying. But eventually, what we want to do is to preserve that. It's going to be sine x of x, where I need to hit this the y-intercept being 1. Sorry, the limit as x approaches to 0, I want the limit to be 1. Okay, so it's got flipped. So what I need to do is to flip again. I want to reflect along the x-axis. That means you want to multiply by -1. Okay, let's do that then. So what I had the trouble here initially was just the linear factor, realizing because I've got the roots of the sine x over x, I can present the polynomial factorization. However, what was causing the trouble? The constant term was causing the trouble. Hence, I just divided by the n pi squared to sort of reduce down the constant term to 1. Okay? Then the behavior was very similar, but then it was alternating, so it was just reflecting. So I wanted to flip him. So what you can do is simply just multiply by the -1. Well, in fact, you don't have to, but if you multiply the -1 for our algebraic manipulation, it just makes a lot of things easy. So what I like to do is just to claim that I can actually multiply by -1 because it was just alternating depending on the number of terms. We saw that first 10 many terms, it was the same behavior, but as soon as I went to the 11th term, then it got reflected. So I want to flip it again. So that means I want to multiply by the -1. Doesn't really matter, but why doesn't matter also can be a very good IA topic. But yeah, so as you can see, since I multiplied the -1, I changed the order of the terms, right? So instead of x squared minus n pi squared, I got the n pi squared minus x squared. That is great. So that is my claim for the sine x over x described by these polynomial terms, well, which is an infinite product, okay? So that is great. So this is a topic 2, because from the topic 2, what you want us to do is to look at the behavior of a function, right? And depending on the size, what you can do is to reduce it by maybe doing some, dilation, right? What I just done essentially is a dilation from the function transformation. And also we are talking a little bit of a polynomial as well, because even though it was a transcendental function involving the sine x, there are some polynomial functions that can actually describe it. So that is a great extension of the topic 2. But not only that, what I like to do is to investigate more with this pi, with this product form, because what we prefer is actually what we haven't learned about the product. What we are more familiar with is the sigma, the summation, right? What we want is actually working with the series. So here's the thing. Okay, so now I've got this function, now I got this polynomial, but describe a bunch of the product, which is very hard to investigate. But if I can actually convert into the sigma, that might be more familiar with me, because I know one or two things about the series. From the topic 1, you talk about the infinite geometric series, and topic 5, you talk about the Maclaurin series. So we do get to learn a lot of a series. And what I can do is to suggest composite with another function that has got the property of converting from the multiplication to the series. Can you tell me a function that converts from the product into series? Can you call yourself? Very good. I'm going to actually composite with the logarithmic function in both sides because of the property of what? Logarithm of the product that gives you the sum, right? So that is a great function to convert my binary operator from the multiplication to the series. So that is great. So let's do so. So I just took the composition of the log on both sides. Now I see that this whole product will actually become the summation using the property of log. Let's see. So all this multiplication will just become the summation, which I then can introduce the sigma notation. There you go, right? There you go. And yes, I can apply the property of the logarithmic function as well, realizing ln a over b is ln a minus ln b. So that is great. So I can also change the left-hand side as well. Let's do so. So, So if I do so, then it's going to be ln sine x minus ln x. Aha, so I see a very interesting series here. Okay, I see a very interesting series here. So what we started with this video, with the topic 2, is the curious case of a sine x over x. We saw the appearance of that function quite often in an IB exam. And we said that because it somehow involves with the solution of Euler's solution to the Basel problem. But what we have not still seen is what number, The main discussion, main aim of this video, whole series, is to talk about the Bernoulli number. Remember that? We wanted to talk about the Bernoulli number. And from the topic 1, we saw the Bernoulli number with the power sum and factorization with the binomial coefficient, and it represented the Bernoulli number as the coefficient of the polynomial terms. But I don't see any Bernoulli number yet, okay? So what we need is a bit of more extension with this sine x over x, and then come back to it, okay? So I'm gonna leave it like that first for now, but we're gonna come back to this series after some more discussion with the Bernoulli number, okay? So let's get to the second function that I'm interested in, other than sine x over x. Let's have a look at this function. So what I want to do is to find this function where its derivative at 0 gives me our Bernoulli number. I want to find function's kth derivative will give me the kth term of the Bernoulli coefficient. Oh, okay, hold on a sec. To get the coefficient with derivative, we saw that idea before. In fact, we saw the idea from the Maclaurin series. Maclaurin series was defined to be with the what? Coefficient as the derivative with the power series, right? So this is a definition of a Maclaurin series. And what I'm saying here is, I want the derivative to be the Bernoulli coefficient, so Bernoulli numbers. I want to find such functions for that, okay? All right, that's interesting. But here's the thing, what it reminds me here is, okay, that's almost what, right? But what we know in the Maclaurin series is the standard form of the exponential function. I know that his Maclaurin series is going to be k is equal to 0 to infinity of x to the power of k over k factorial. That is, what is it? The exponential function's Maclaurin series. It almost looks like that, right? Other than the product of the bk, the Bernoulli number. Okay, so maybe it has something to do with it. Maybe it's something to do with it. And so what I want to do is to find that function. I want to find that fx. Okay, so that is great. But in Maclaurin series, yes, as you can see, we see this definition of the exponential function using this power series, and maybe we almost have it. It's looking very, very similar other than the coefficient. And let's see what we can do, how we can actually associate with this exponential, almost exponential form with this function that we would like to actually derive. Okay, let's have a look. And for that, we need something fancy. Yes, it's not in syllabus. This is not in syllabus, but it's something required, okay, to make things easy. And obviously, very, very good IA topic. Okay, if you're interested in, you can talk about the cost product and talk about more extension from it. So what I like to show you is this. You don't need to know the details yet. You know, it's not really the time for me to talk about the cost product, but what I'm telling you is I need this to derive the function that we wanted to get that has got the derivative being the Bernoulli number. Okay, so what I like to show you is this. Okay, imagine this power series, right? Imagine this power series, and what the cost product suggests is that the product of this infinite series, the product of this power series can be actually combined together. When you do so, this coefficient ck is defined by another series of the following. Okay. But if I quickly show you, what this really means, it's really just a distribution. This is really distribution. This is really distribution. Because, you're going to have a bunch of the a term, let me just write it as a1, x1, to the power 1, blah, 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 and then b1, x1, plus, with the constant term a naught, b naught. And then what you're doing really is just a distributing, right? So you're pairing those coefficients with this distribution, okay? So obviously detail has to be thoroughly studied, but I'm just showing you just rough definition. But I'm not going to talk about this in details, but what I want you to do is I want you to accept this technique, right, to discuss further. So I want you to pause the video, just write down the identity. Have you done that? That's great. So let's get into it. So how can I use this cost product for what we wanted to discuss? So what we wanted to get is this fancy function, right? We wanted to get this fancy function and hence define this Bernoulli number, right, as the derivative. Okay, and then it almost looked like the exponential function. And what I want you to do is, if it's almost looking like that, and what we have just done the cost product, what I would suggest is that you simply just multiply these two functions and see if you can actually combine using the cost product. Let's see. So that is the function that I don't know, right? And then that is the Maclaurin series of the exponential function. That is great. But now what I like to do is to combine them. I want to combine them. Okay, using who? Cost product, right? This is the cost product property, right? It was if I quickly remind you again, it looks like this. The ck represents the sigma of AL bk minus L, AL bk minus L, and that's what you see here. It is really AL bk minus L. Okay, so that I'm using the cost product, and what I like to do is to see any similarity, any familiar appearance of the expression here, any family expression here. What I want you to see is that, all that, I want you to pay attention to this. I want you to pay attention to this. Okay, where have we seen that before? Where have you seen that before? You're absolutely right. We actually have seen it from the binomial coefficient of the combination. What we remember from the combination is n choose k is simply who? Is n factorial over n minus k factorial times k factorial. So if I look at this I factorial and k minus I factorial, that's almost the binomial coefficient, right? Okay, so what I'm combining here right now is this. Look at this. By using the cost product, I found this ck, right? That's the combined form. And in fact, I can actually combine this power function here. And I want you to realize I and negative I just cancels out, leaving just x to the power of k. That's great. So the bi, which is the Bernoulli number, is on the top, and then on the denominator, I got bi factorial k minus I factorial, which then can be given as what? What was missing? What was missing for this one to become the binomial coefficient? K factorial was missing, you see? But I didn't have it before, so you need to essentially divide this by k factorial, but that part can be actually put into the binomial coefficient. That's great, but you still have to divide this by k factorial because I didn't have the k factorial before. Okay, well, hold on a sec. I got the binomial coefficient and then the Bernoulli number. Remember from the topic 1 video, from the, from the power sum, we divide by 1 over n plus 1, and then we factorize by the binomial coefficient, and the left remaining term was actually in the multiple of the Bernoulli number. We see something like that. Okay, that's astonishing. That's great. Okay, that's great. And what we want to do is to to discuss this further. I want to dig in further. Let's have a look. So what I want to do is to talk about this CK, right? So I want to still talk about this CK. And let's see what more simplification we can make, okay? So returning to the power sum definition with the Bernoulli number was this, right? That was the definition that we did, right? 1 over n plus 1 binomial coefficient gives me the Bernoulli term, all right? So now with this Bernoulli numbers, right? That is great. But if I let n equal to 1, right? What this means is that I'm adding 1 to the power of m, which simply just becomes what? Which simply just becomes 1, right? Okay, so left-hand side, if you let n equal to 1, will be simply 1, okay? But on the right-hand side, if you put n equal to 1, what you see is who? Sure, that will be 1 from what we just have said, and that will be simply 1. So I'm just only having this summation here, which then I have like the following. And I can actually rearrange this n plus 1 to the other side, getting this n plus 1 is equal to summation. So that is great. So this summation of the Bernoulli numbers gives me n plus 1. Okay, that's interesting. That is interesting. So from that, what I like to do is to make further substitution. Instead of working with just n plus 1, I'm going to let the n plus 1 to be k. Okay? If I let that to be k, then everything with the n plus 1 or in terms of m can be described in terms of k, which I have it as the following. And then why have I converted this way? Because we had, what is it? The ck of the following. So from this Cauchy product, I just multiply the function and exponential function and managed to use the Cauchy product to derive this fancy ck. This was the fancy ck, okay? And from that fancy ck, what we also saw more was almost with this term, right? That term, using the partial series, this says this term says to add from 0th term to the kth term. But using the partial sum, what I like to do is from adding 0th term to k minus 1 term, and then add the kth term. So what I'm saying here is that Sn is the same as who? Sn minus 1 plus An. That's what I'm really saying. So instead of adding k up to k many term, what I can do is up to add k minus 1 many term and then just add the last term by itself. But what we saw before from using the the definition of the power sum with the Bernoulli number, we saw that this actually became what? This actually became just simply k. But we saw that, right? We saw that. We saw that from the power sum definition. Okay, so then this fancy ck can be actually described what? This fancy ck can be described as the k plus bk, where bk is the Bernoulli number after the kth term. Okay, that is great. So from this product, we use the Cauchy product to derive this, and from this fancy ck, I managed to convert into the k plus bk. Okay, all right, that is great. And what I want you to do is just simply distribute it before expanding with the sigma. If I simply distribute, what I get is the, k over k factorial, so k cancels out, so I only have k minus 1 factorial using the recursive definition, and the bk times, so look at this, by using the linearity of a sigma, I got the sigma bk x to the power of k over k factorial, but remember, that is the function that I wanted to find. So for that, I just define it as the fx. And if you look at the first term there, what does that remind you? What does that remind you? You're absolutely right. By using the change of the index, what I want you to know is that's just x times exponential function, right? Because remember, e to the power of x is who? Sigma x to the power of n over n factorial, right? Starting from 0 to who? Infinity, which is the same. Remember, which is the same as sigma 1 to infinity x to the power of n minus 1 over n minus 1 factorial, which is almost what we have. But then remember, I got the x to the power of k because I can just simply multiply by the x on it. So that is just the Maclaurin series definition of x times e to the power of x. Oh, hold on a sec. So what was the left-hand side? This journey was started with just left-hand side being the fx. And using this fancy Cauchy product and all that, what we actually ended up having is this fx is equal to simply the x times e to the power of x plus fx. Oh, wow. Okay, you can actually perform more rearrangement to get the following fx function. So what I like to do is just rearrange to the other side. Hold on a sec. Doesn't it just cancel out? Hold on, my bad. I think there's something that I need to fix. Because in order to have that denominator, I know it needs to be in the product of the exponential function. So give me 1 second. What has been done wrong? Sorry, my bad. Everything here started with this, fx times exponential, right? So that was the left-hand side, my bad. So here, everything started with the fx times e to the power of x. Okay, that's great. So that was what's on the left-hand side. So that should have been modified. So here, finally here, we had e to the power of x, right? That's where we used the cosh product to combine together and then got the right-hand side simplified form. Okay, so now if I rearrange to the left-hand side, what you get is, I can factorize by the fx, then I have e to the power of x minus 1 becoming x times e to the power of x. And if I shift that to the other side, I get this following function, where his derivative will give me what? At 0 will give me the Bernoulli number, okay? So that is what we can do. So what you need to do with this deriving method is to understanding what it means by the cosh product, right? And that can be acquired definitely by the practice. The reason, therefore, I came up with this function is because we wanted to come up with the function whose derivative at kth term will give you, kth derivative at 0 will give you the kth term of the Bernoulli number. We claim, we wish to have it, and we can actually derive it, right, using the algebra and the function definition. So that is great. So now I want to simplify this further. So let's try to divide this numerator and denominator by exponential function e to the power of x, and what you end up having is simply just this function. And that is known as the generating function for the Bernoulli number. Wow, very fancy. Another good IA topic for you, okay? And can we separate them? What I want you to notice is that this fx actually can be separated like this. If you put into the common denominator, you actually end up having the same thing. Okay, so that, my friend, is another version of that function whose derivative again will give you who? The Bernoulli number at 0, at x equal to 0. Wow, that is a great journey. So for the topic 2, what we started was what? We started with the sine x over x, right? We put it into the polynomial form with the product, right? Bunch of the polynomial term with the product, and then came up with what? We actually came up with some fancy series of what? Ln sine x, right? We actually came up with the ln sine x with bunch of a series with the logarithmic form, whatever, right? That is great. And then the next thing that we did is, okay, we put a hold on onto it. Don't worry about it. We are actually going to come back to this, but then we managed to get this from our understanding with the function. And the third one that you're going to do is with who? What was it? It was our wish. We wish that this function would exist so that, his coefficient will be, his derivative will represent the coefficient of the Maclaurin series, and in fact will be the, the Bernoulli coefficient, right? And then we use, we use the Cauchy product, the fancy definition that it's not in the syllabus, but that can be definitely taught for your, IA or EE, and then came up with this function, right? It was, I believe, was one of the generating function. What was it? The x over 1 minus e to the power of negative x, that is great. But for what? Right? What do we need to do? Is going to be the next discussion for topic 3. So hold on a second, hold your breath onto it. We're still getting there. It's supposed to be everything, everywhere, all at once. What we are trying to build up is to the solution of the Bernoulli number with the zeta function for the even term. But these are some preparation that we need to do. And now what we're going to do is to somehow connect this idea together with the idea of a trigonometry in topic 3. Okay? So please try to make some notes and summary of what we have done so far for the topic 1 and topic 2. Now let's get ready to move into the topic 3. Okay? That's pretty much it for me today. See you in the next clip. Hello friends, let's have a look at the link with the Bernoulli number with topic 3 trigonometry. So what we have done so far from the topic 1 is the introduction of the Bernoulli number with some Pascal's triangle and binomial coefficient. And topic 2, we came up with fancy function sine x over x, and we came up with the product expression made into the summation with the logarithms. And then we came up another great generating function such as x over 1 minus e to the power of negative x, whose derivative at 0 will give you the Bernoulli numbers. And what we want to do is to combine them together with the understanding of a trigonometry. So let's get to it. Okay, I love her. You know, she was one of the supporting role for the movie, and she played it really well. But anyways, let's get to it. So connection, right? Topic 3, the reason why we are learning the trigonometry is to build a bridge between the real and imaginary, and between something with the discrete and continuous. Okay, so what we want to do is really want to build a bridge using the trigonometry, and let's see if that build can be also made between the Bernoulli number and later on the zeta function. So let's get to it. So what we are going to do is to actually play around with the generating function that we derive, right? With the Cauchy product, right? Very fancy product. And what we want to do is to show that his nth derivative will give me the Bernoulli number. Okay, let's play around. So it's supposed to be the coefficient will give me the Bernoulli number, and then we know the list already using the the power sum and bit of expansion. We managed to find the first term being 1, negative half, 1 over 6 is 0, negative 1 over 30, and 1 over 42, etc., etc. Okay, so that is great. So if I use a differentiation to find the list of a coefficient, we get the following expression, right? So that is what we have, and we got this term. But here's the thing, if you compare with the terms that we already had, this coefficient of a linear is a little bit suspicious, because I know from the list, as you can see, what we see here is that B0, B1, P2, in this series, I got 1 half, 1 over 6, 0, negative 1 over 30. However, what we saw before was the B1 was who? Negative x, negative 1 over 2. So in fact, this should have been, what is it? Negative x over 2. Okay, so that is interesting. So some alternative version of the Bernoulli number gives you B1 as positive half, and some gives you negative half. But we want to work with the negative half for this practice, for this question. But you can also elaborate this idea for your internal assessment or for the extended essay, why positive half or negative half sometimes has to be defined alternatively, right? So that's a great discussion. But at the moment, we want to have the B1 as a negative half. So that's the premise. Okay, so what I can do is, okay, I had a positive x over 2 that gave us B1 as positive half. But if you subtract by x, this 1 over 2x, if you subtract by x, I will have negative x over 2, which then results that we do have the desired B1 to be negative half. So that's great. Everything else is the same. So what I then is, okay, I need to redefine my function, the generated function that we got it from the previous part, as the following. So I just subtract by the x. Okay, so it's not big of a deal. It's not big of a deal. In fact, the previous definition wasn't so wrong, because sometimes you define it for the positive half, sometimes you define for the negative half. But for our purpose, I want to work with the negative half, so that's why I subtract by the x. It's not a big deal. Okay, so that is great. All right, so that's my new generating function of this Bernoulli coefficient, Bernoulli number. And we just checked that his kth derivative at 0 will give me the, what is it? The Bernoulli number. So that is great. Okay, that is great, with the B1 being negative half. So that's great. Okay, and in fact, what we noticed something in particular is that, look at this. Okay, other than linear, I only have the even degree, right? That means the odd degree will always have the 0 coefficient. So that is great. So the case of B1 is, again, is interesting. Sometimes we state for the half, sometimes we go for the negative half. You can actually investigate this further if you want, right? For your IA or E topic. And then also, what I notice is that for up to 10th term, all the odd terms seems to be 0, other than the first, for the degree 1. But can we actually prove that it is going to remain 0 for the case of an odd case, right? So that's another discussion for your IA, but that's not the aim of the lesson at the moment. I'm going to accept that it does become 0 eventually. I mean, starting from n equal to 1, and the odd term is to 2n plus 1. Okay, so I'm just throwing out some further investigation for you as we go by, okay, against all the odds. So let's have a look. So can we rid of the odd term by adding what? So what we had was a great generating function, but now it has a very lonely odd term, which was negative x over 2. Okay, but why don't we then set him free? By getting rid of him and only discussing with even terms. To do so, remember that odd term was only the negative x over 2. To get rid of him, I would just add by his opposite sign, which is a positive x over 2. So now, if I let this to be my new generating function, it's only going to involve with what? It is only going to involve with the even terms. So now this new function only contains what? Even term, because the odd term will actually cancel out. Now I only have even terms. So that's my new function. That's my new function. Okay? So this is my new generating function. That involves only even term. Unfortunately, his derivative does not give you the Bernoulli number anymore because you got rid of the odd term. Okay, but let's talk about it. So what I want you to do is try to put into the common denominator. So if I do some algebra, I got the following, okay? And what I want you to do is, in fact, divide this by e to the power of negative x over 2, top and bottom, which is essentially multiplied by 1. So I'm not really changing anything, am I? So then I get this sort of a fancy-looking function. All right, that's very fancy. I got the exponential function. It looks like it's conjugate with the negative. Okay, but I got the sum and difference. Do you remember where you might have seen before? And in fact, these functions are very, very popular again for who? Paper 3. It already happened since 2021. It already happened twice with the hyperbolic function discussion on such function, right? So it's very important for you to know it actually, even though it's not in syllabus. It's very popular for exam questions such as a paper 3. So let's have a look at those functions actually. So what we actually are going to talk about is one with the complex number. Okay, so for the older form, we know e to the power of I theta is defined as a cosine theta plus I sine theta. And in fact, we can use this definition to describe for the cosine and sine, right? The sum of complex number and conjugate divided by 2 will give you only the real part, which is a cosine theta. And difference will give you the imaginary part, which is I sine theta. Okay, that is great. So that is another representation of a cosine and sine with this complex number. Okay, so that's what we learned in the syllabus. But what you can actually develop further is the following form. So that is the discussion we had, isn't it? But in fact, in this time, you know what? I like to make a fancy substitution with the theta. I'm going to substitute with ix, where I is the imaginary number and x is a real number. Okay. Let's see what we get. We know I squared is negative 1. So if you actually, well, hold on a sec. Yes, you might say, is it possible? Is it okay for me to substitute with the ix? Shouldn't I define things then if I wanted to work with the imaginary number? You're absolutely right. Obviously, we can investigate further for who? IA. But let's suppose it is true. It is okay. Then what I see here is that if I put it in the sine theta with the iz, oh, sorry, it's supposed to be ix, my bad, right? If I plug it in, then you see that it's going to be ix and ix, but then it makes the I square becoming negative 1. So then I got this following. Well, I don't like having the imaginary number in the bottom, so I just rationalized, then becoming just what? Negative I, where I put the negative here to change the order, and that, my friend, is the, what is it? Another expression for the sine iz, and that is the representation of the hyperbolic sign. It's not in the syllabus, but very funny, happens so many times in the paper 3. So in fact, you should learn it. You should learn it, okay? Okay, so that is the definition of a hyperbolic sign. Who is a hyperbolic sign? This e to the power of x minus e to the power of negative x over 2, that's hyperbolic sign, okay? And you can do the same thing from the cosine. If you actually put the ix, you actually get the hyperbolic cosine. Okay, so if I define for you, hyperbolic sign is defined to be the difference of the exponent and its conjugate, and then the cosine is the sum, right? Very similar to the definition of a cosine and sine with the complex number. And you can do the vice versa. So that is great observation. That's a great observation. Even though it's not in the syllabus, yes, very, very popular, has been and will be for paper 3. So I strongly suggest that you learn it, okay? So that is great. So let's have a look at our initial expression. That what we had was this generative function that we derived, but then added by the x over 2 to get rid of who? Very good, the odd term. So now I'm only dealing with the even terms, all right? So that is great. And we had this fancy top and bottom by, dividing by e to the power, I think it was negative x over 2. And then what you notice is that, oh, okay, that's a hyperbolic cosine, and that's a hyperbolic sine, right? That is great. So, over 2 just cancels out, no more problem. Then it becomes a hyperbolic cosine of a hyperbolic sine. But just like the sine cosine, the cosine of a sine is a cotangent, sine of a cosine is a tangent. If I see the ratio between the hyperbolic cosine and hyperbolic sine, we call it hyperbolic cotangent. Okay, that's very fancy. Right, so what I can then see is that, this generative function with the x over 2 can be defined simply by this hyperbolic cotangent function of x over 2. So there's a great link between, again, with what? Bunch of function with the trigonometric function, hyperbolic function, right? So let's have a look. So what I can then define is that, okay, that is going to be simply that x over 2 times cotangent x over 2. Right? And remember, that was what? In fact, the one with the derivative that gives you the Bernoulli number, we already know his power series. We already have discussed the power series for him, right? We already defined the power series of this, which was represented by the series with only the even Bernoulli coefficient. Okay, so which was this? So as you can see, I derived this using the substitution of the hyperbolic function. And in fact, we can use the the power series that we already have defined from the gx plus x over 2 from topic 1 and topic 2. That means I can actually find the the power series for this x over 2 times hyperbolic cotangent of x over 2. So that is great. But obviously we don't want to write like this. We want to obviously describe using the, the sigma notation. And remember, this term, what we are giving is only the even terms of Bernoulli number, right? Such as B0, B0, B2, B4, B6 divided by who? 2n factorial. So that is the definition of this function with the sigma definition, which only deals with, again, the even Bernoulli term with the even degree polynomial divided by 2n factorial. So that is great. Okay, and what we can do actually, we can simplify further, meaning, I can just rearrange the x over 2 to the other side and maybe just divide by the x and multiply by 2. And then instead of dealing with the fancy x over 2, I can make it as x by, substituting the 2x on top of the x, right? So, I always prefer working with the simpler version. So let's try to make some substitution and algebraic manipulation to simplify. So let's have a look. So, what we want to do is to get rid of the x over 2, by rearrangements first. So let's try to rearrange this to the other side. What I then end up getting is just multiplying by who? 2 over x, the reciprocal, but, it's going to be term by term, so it actually gets multiplied on every term of the sigma, of the sequence within the sigma. So, it just cancels out, so it becomes 2n minus 1. And I divide it by, so I multiply by 2, but it's a constant factor, so I can actually take him outside of a sigma. Okay, so far so good. And what I want to do is, instead of working with this fancy x over 2, if you replaced x with 2x, it would cancel out, isn't it? So what I like to do is, in fact, composite with the 2x on the x, right? So that's what I'm doing. I'm compositing the 2x on it. Okay, so by using the laws of exponent, I can actually expand them as a 2 to the power of 2n minus 1, x to the power of 2n minus 1, right? And here's the thing. That's still a very fancy series for the hyperbolic cotangent. Now, what are the odds? What are the odds for us to work with the hyperbolic function? I'm more familiar with the trigonometric functions such as sine, cosine, tangent, secant, cosecant, cotangent, righto? But here's the thing, okay, so I've got the hyperbolic function, but I want to back into the trigonometric function. Then what have we done? What have we done if I wanted to move from the sine hx hyperbolic sine to sine x? You're absolutely right. We made some fancy substitution with the complex number, didn't we? If I substitute with the ix, we somehow managed to see some multiple of imaginary number with the sine. So that is great. So what my bet here is, what my guess here is, what my claim here is, if I make some substitution with the ix on the x, I should be able to actually convert into the trigonometric function. Just like we saw from the hyperbolic cosine to sine, cosine, hyperbolic sine to sine, I want to do the substitution with the ix and see if I can convert again from hyperbolic cotangent into cotangent. Let's have a look. So we're going to actually try. So if I make this substitution to convert, let's see, this is a hyperbolic cotangent. So that's the hyperbolic cosine over sine with the ix. We already know the definition of a hyperbolic cosine and hyperbolic sine with the exponential form, but I'm now replacing with the ix. Oh, hold on a sec. That is actually what? From the complex number, if you add complex number and conjugate divided by 2, you only get the real part, which was a cosine. And the difference will give you the I times the imaginary part, which is this. Well, hold on a sec. Cosine over sine is a cotangent function. And from our guess, yes, it was correct that I can actually convert from the hyperbolic function into the trigonometric function by substituting with the complex number such as ix. That is great observation. That is a great observation. That means I can actually do the substitution for my power series to get the power series of a cotangent x. Let's have a look. So from this, now I see from my power function of the the hyperbolic cotangent, I'm going to substitute with the ix here right now. Okay? Then I know it's going to actually become the negative I times cotangent function. Okay, so far so good. Obviously, we want to do more simplification, so I just expand the exponent. And here, especially for I to the power of 2n minus 1, you realize that, you can realize I to the power of 2n is just an alternating term. That's great. And then if it's minus 1, you are dividing by the I. By rationalizing, you know that it becomes negative I times negative 1 to the power of n, right? But then now I see, okay, so that is going to be replacing that. And you realize the negative I multiple is a left and right. You can actually get rid of it by the common factor, right? So then you end up having this following expression for who? Cotangent function. In fact, now we realize, I can describe the cotangent function as this following power series with the Bernoulli number, even term, such as B0, B2, B4, B6. So that is a great observation. How have we got this? We used the generating function from the topic 2, which was what was it? X over e to the power of x minus 1, and what was it? Minus x. But then we wanted to leave out we only work with the even term, so we added the another x over to cancel it out, and then that generating function gave us a whole bunch of the even term of the Bernoulli number. And using some trigonometric identity as well as the complex identity, we managed to conclude here. And that's why I say topic 3, the trigonometry is a connection. You get to connect between the real and imaginary numbers, between the real and complex, okay? So that's why we get to study trigonometry a lot, because it's a strong, strong bridge for every island that we want to go within the AA syllabus. So that is a great observation. But we are not done. What we want to do is to use that observation finally for topic 5 with bunch of differentiation, bunch of integration. Okay? That's pretty much it for me today. See you in Everything, Everywhere, All at Once in topic 5. Hello my friends, let's have a look at topic 5, everything. So this is the bagel. It's one of the main sort of a philosophical idea in the movie called Everything Everywhere All at Once. And if you're keen on movies, I think you're gonna love the cinema, but it's the main things. And what we are gonna do is to associate this everything with the calculus, right? The calculus is really just everything what we do in AA syllabus. And let's see what connection we can make, okay? Right? Let me quickly remind you what we have derived from the topic 2. Yes, we wanted to talk about the curious case of a sin x over x, the very popular function to deal with for the exam questions. And then what we saw was that, okay, sin x over x, I can actually describe this, product of the terms, right? Product of a polynomial terms, but we didn't want to work with the product, so we wanted to put it into the series, and that's why I put a logarithmic function on it to derive this series. That's what the conclusion was in the topic 2, right? And what we're going to do is actually investigate this further. So let's get to it, okay? and then develop for with the calculus, especially with the differentiation. So yes, what I can do is to simplify the left-hand side, which becomes sine x minus x, right? So that is, sine x, ln sine x minus ln x by the property of log, right? Okay, then if I rearrange the ln x to the other side, I see this fancy polynomial, well, not polynomial, sorry, but fancy infinite series for the ln sine of x, okay? But here's the thing, in the calculus, we see this function all the time. In fact, if you look at this integral, do you remember how to do this integral? You're absolutely right. This is actually integration by substitution, right? So if I, put this in the quotient form as an integral of who? Cosine x over sine x dx. If you make the substitution u as a sine x, you can derive this, right? Because you actually end up having just 1 over u du, which you know by the fundamental theorem of calculus, it's the ln absolute value of u plus c. I'm done, right? Thank you. So that's great. And what we see is, okay, so, it's something to do with the integral of a cotangent, okay? And by the fundamental theorem of calculus, then you know that the derivative of a logarithmic sine x is going to be simply cotangent x. Okay, plot thickens. The story here is getting more interesting. The plot is thickening, okay? So let's see. So what I want you to do is, okay, so that was a series that we derived from the topic 2. And what I want to do is to actually differentiate these both sides. So let's try to differentiate. So by using the fundamental theorem of calculus, we managed to do this integral. So now I can see if you differentiate, you can actually check yourself by using the chain rule, right? That does become cotangent x. That is great. So on the left-hand side, I just have a cotangent x. But on the right-hand side, if I differentiate on the right-hand side, it's going to be term by term differentiation, and the first term is pretty trivial, right? It's a logarithm, so derivative is simply 1 over x. That's great. But I want you to realize on the right-hand side, that's infinite series. So you are actually going to differentiate one by one, right? So you need to differentiate this term, general term, right? But it's a logarithmic function. And from the logarithmic function, we know that we're going to use a chain rule. Remember, ln fx, if you differentiate, what do you get? It's going to f prime over f, isn't it? That's what I'm expecting for that one, right? If I differentiate. So, let's do that, right? So, yes, I'm going to do the term by term differentiation. That's what I'm about to perform. So if I do so, we know that it's by the chain rule, and let's see what we get. Look at this. So I will leave it as an exercise. This is simply really just a simple chain rule method. You should be able to do it actually, right? If you can't, that's not good. So make sure you're able to do that by doing the exercise. But let's have a look at this. Okay, so that form just simply became this infinite series. Easy peasy, lemon squeezy. So now we solve from that one, and by the fundamental theorem of calculus, that became just simply cotangent x or the chain rule. And then on the right hand side, we managed to convert this sum using that one, and ln x is trivial, just 1 over x. And if we have this therefore following infinite series for the cotangent. Hold on a sec. At the end of the topic 3, we saw this fancy cotangent power series with the Bernoulli coefficients or Bernoulli numbers using the fancy generating function from the topic 2. But I'm using the topic 2 discussion, the generating function. Well, not generating function, sorry. It was from the sine x over x, right? It is also generating function, but sine x over x. And I'm trying to make some comparison. This is a little different from what we have derived from the previous video. But it's okay, let's actually simplify further. So I want to dive deeper on this one, right? So let's have a look. Let's look at the next slide. So yes, in the topic 2 for the AA, is it topic 1 actually? Partial fraction is in the syllabus for the HL students, yes. And yes, if I look at this linear of the quadratic, which is a factorized form, I can actually let the remainder to be constant and find the A and B simultaneously. And you can do the same thing for our series. Look at this. This was our series, but look at this. It's got the linear, it's got the quadratic, which was actually the difference of a square, and you can do the difference, you can do the partial sum. You can actually do the partial sum to derive this, okay? So that is great. So what I've just done now is just use the partial fraction that we learned in syllabus. So this is why this question is so great, because every bits and pieces are within our syllabus. That is great. Only the overwork was the Cauchy product. And And I'm about to show another extension that is needed. So I'm going to mention it, but you can obviously investigate further for your IA topic, okay? But let me quickly show you. Before actually talking about the extension, this can be actually simplified further. You know, what I want you to do is simplify these two terms by 1 over n pi. Then I get this following algebraic expression. But here's the thing, you know, I want you to realize if you see anything similar with these two terms, right? Look at this, 1 over 1 minus x over n pi. Okay. What we remember from the topic 1 is what about this? Infinite geometric series. First term over 1 minus common ratio. First term over 1 minus common ratio. Okay, so what I then claim is that can actually be described by the infinite geometric series. But of course the question is, can you? Shouldn't you be careful within the interval of convergence? Whenever you want to throw out this type of definition, you always have to mention about the interval of convergence, right? So it is your job to claim that, okay? Let me just write it right away. So yes, I'm just trying to use the infinite geometric definition to express them. So for this one, my common ratio will be negative x over n pi, where you know that the common ratio must be between negative 1 and 1. And then I can actually define it as a infinite series formula, right? Of the infinite series summation. So for this one, the common ratio is going to be x over n pi. Then I don't have any alternating terms. This is what we get. And then where have we got this from? Yes, let's have a look. Where we have got this from is from this series. Within the sigma, I can describe another sigma. Okay, so that is great. Let's have a look at this. Okay, that's what we see within sigma. I see another sigma, which is called a double summation, but which is not in the syllabus. So that's why I said I need extra extensions. The first extension we talked about was a Cauchy product in the topic 2. And for the topic 5, I need the double summation, for which it's not really challenging. You can actually learn it. It's just not in the syllabus, okay? So let's have a look if I can see any cancellation, if I see the difference, right? So let's have a look. What I like to do is to expand this alternating series, which I just get that, and I'm looking for the difference. And as you can notice, there are quite a few terms canceling out. 1 cancels out, square cancels out, or in fact, all the even degree cancels out. Only the odd degree remains, and it gets actually double. So that's why I factorize by the negative 2, and then write down the sum of the odd terms. Okay, that is great. So that's what I've got. Still can be described as a sigma. So let's go back to the sum that we wanted to talk about, right? So this was the fancy summation that we found, and all that, what we saw was that it can be actually described as infinite geometric series, which we just did, right? And then we saw that what the sum cancels, the even degree actually cancels out. I can actually only arrange with the odd terms, right? Odd degree terms. So this is what we have. Okay, that is great. So far, so good. Okay, but here's the thing, you know, what is this, right? It's talking about the index of k, and it's talking about the index of n. It's got n and k, it's got n. It's complicated. So it's a double summation for which you can get used to. So changing the summation, it's not that bad at all. You just have to make a suitable substitution. But for now, I'm going to just mention the technique because it gets very lengthy if I have to explain. But I will leave it as an investigation method, okay? As an investigation task if you're interested in actually proving it, right? But if I just show you the method, right? So let us expand the bracket. What I want you to do is just expand this bracket here. So I got the x to the power of 2k plus 1, x to the power of 2k plus 1, pi to the power of 2k plus 1, all right? And what I want to do is to combine this in here. And if you ask me, is it okay? Well, it's an accidental mistake that happens to be correct. This is what I'm going to put it. Because we haven't proven it, so I can't really use things like that. But I'm going to just use it for simplification of this method, okay? So what I want you to do is, okay, I'm going to just take this inside here, where then I'm raise the power by 1, so it becomes 2k plus 2. And I'm raising the power of this by 1 as well, so I got the 2k plus 2. Okay, so that is great. And so this is what I've got if I combine that n pi in the sigma, okay? And then what we can do is to change of index. What I mean by that is, look at this. If I start from 0th term to infinity, I have a0 plus a1 goes all the way. But if I want to start with k equal to 1, then I have to just change the subscript as a k minus 1. Then if I plug k equal to 1, that becomes a 0, 1, 2, 3, 4, on and on and on. I can do that. So what I like to do is instead of starting from 1, I'm going to start arbitrarily k equal to 1. But for that, you need to change everything by k minus 1 for your sequence. So what I'm saying here is if I replace this with k minus 1, 2k minus 2 plus 1 becomes 2k minus 1. But everything else will be simply 2k. That is great. Okay, so that is great. So what I have now is, okay, I had the 1 over n pi, I put it inside and changed the index from 1 instead of 0. Okay, so I got this. But you know what I'm going to claim without proving, because I don't want to make this video extra lengthy, but here you need something called a double sum. And it changed the order of a summation is what you need to understand. But I'm not going to explain it, unfortunately. But I just want to quickly show you that I will flip it. Look at this. From here, I just flipped it. Look at this. N and K instead of K and N. And then I will let you do the investigation if it's possible. And if so, how? But I'm going to just use it for free. I'm going to use it for free, unfortunately, because it's an extension. Okay, but if I did, look at this. Okay, so my first sigma tells me that I have to work with the n. And the only term that's got the n is this fancy n to the power of 2k. Okay, so let's just try to sort of pair him out with the sigma. So if I did, yes, that's the sigma that I wanted to get. But as you can see, that is what we have defined for the zeta function. Right? This is actually zeta of only the even term. Okay, that's really interesting. Sure. So as you can see, I just paired this sigma with n with him, and everything else with the k with the k. Okay, is it possible? Double summation, something that I need to accept for free. Although if I was writing for the internal assessment, of course you have to explain, but that's not the purpose of this video, okay? But yeah, that can actually be re-expressed as a zeta function, isn't it? So let's do that, right? So now of that one, I'm going to use my fancy notation of a zeta function over 2k. So that is great. So if I did, my cotangent function can be described by this power series here. Oh la la, oh la la. So where did this journey start? What we had done in the topic 2 with the fancy function of the sine x over x, we came up with the product. We put a log on both sides, put it into the series, and then we did a bit of a rearrangement, and we found the series for the ln sine x with a bunch of a power series. And then we used the fundamental theorem of calculus to differentiate to both sides to get something of a cotangent in another form of a Maclaurin series, for which we just did, okay? But from the derivative, we used the geometric series to simplify the summation within the sigma, and then use something called extension with the double summation to change the order of summation, etc., to came up with this nice expression with the zeta function, okay? So far, so very good. Okay, now let's then try to do the comparison, right? From the topic 3, with the hyperbolic function, with the complex number, we managed to find the expression of the power series of a cotangent as the following. And from the use of what? Cotangent and differentiation of the ln sine x, we came up with this series. What I'm going to do is to compare it. What I'm going to do is, in fact, compare it. I'm going to claim that they are equal. Can you claim, even though different looking polynomial, if I can actually make them equal, can I actually equate them? I don't know. It's another investigation for you, for the IA or EE, isn't it? So now, for this one, it starts from 0 to infinity, but to compare with the other one, which started from k equal to 1, I believe, wasn't it? Let me quickly show you that. Yeah, it starts with k equal to 1. I want to start this, this is starting from 0 to infinity. Let me just take out the first term, and then let the sigma notation starting from k equal to 1, okay? So which I can do, right? Because Sn is what is it, my friend? It's a A1, A2 going all the way to AN, which it's going to be, what is it? A1 plus, sorry, if it's a A0, which is going to be then, what is it? A0 plus sigma, k is equal to 1 to n of ak, right? So that's what I'm about to do, right? So instead of working with the 0, I like to matching with the other one, so I'm going to start with k. So if you just take out the 0th term, it's just, 1 over x, right? That is correct, because if you put 0 on it, so x to the power of -1, That's 1 over x, and b naught was 1, and this is 1, this is 1. I got just 1 over x. That's great. And that's what we have for the n equal to 1, right? So now what we're going to do is just equate this series, right? So this is from where? I believe this is from topic 2, right? Sorry, topic 2. And this is from what? Topic 5. This is from topic 5, and this is topic 2. I'm going to connect this understanding and make them equal to. Okay, so what I like to do is compare the coefficient of x to the power of 2k minus 1. You know, I use the index of that sigma as n, but it doesn't matter if you change it to k, as long as it's got all the number of terms, absolutely fine. So now, you know, 1 over x just matching, so that's fine. I'm going to just matching the coefficient of x to the power of 2k minus 1. So let's do that. So if I just derive the coefficient of x to the power of 2k minus 1, left-hand side got this term, right-hand side got this term. Okay, don't forget the negative 2. So don't forget the 2. All right. And our aim was what? To describe the Bernoulli number of the even term. Okay. Or in fact, zeta function of even term. So what I'm going to do is just rearrange to the other side, right? So if I rearrange, what you actually end up having is this zeta over 2k described by the even term of the Bernoulli numbers. Marvelous, marvelous. We actually get to prove it. We prove this using the, again, I think this was topic 2, yes. And this again is who from topic 5, okay? Of working with the cotangent. Easy peasy, lemon squeezy. So let's then see. Okay, so what is the zeta of 2k? Again, that's the zeta function of even term, so 1 over 1 to the power of 2k, 1 over 2 to the power of 2k, etc., etc. That is very good. Beautiful. Okay, can it be negative? Well, I'm adding only the positive term. It's got to be positive. So to avoid this confusion, what you want to do is to lose the alternating term, put an absolute value on the Bernoulli number, and that is going to be a great expression for the zeta of 2k. And that's what you get to see often. And that's what the question that captures everything everywhere AA wants. Okay, so that is a great journey. Okay, so can we apply this formula to a famous result? What's a very famous result for the zeta function? The Bazet problem, right? So that's what we see. And how do you describe this as a zeta function? That's just the zeta of who? 2. That means for the zeta of 2k that we found, I just have to let k to be 1. If I let k to be 1, zeta of 2, if I let the k 1, that's just 2, pi squared and 2k. And then b2 was, absolute value of b2 is in fact 1 over 6. Okay, well b2 was b2 was 1 over 6, so that's great. And therefore, what you get is this famous result of a pi squared over 6. And then what's so beautiful about this is in fact you can do for who? Zeta 4, zeta 6, zeta 8, etc., etc., as long as you know how to figure out the Bernoulli number, for which we do know. Okay? So that is great. If you ask me, how do we derive the Bernoulli coefficient? Oh, well, you know the generating function, right? So you have the x over e to the power of x minus 1, so you just have to differentiate n many times to get the n many terms of the Bernoulli number. So that's great. And that is how we're going to work on it, right? So far, so very good. So yes, that's everything, everywhere, AA once. So what we had done was to talk about the Bernoulli number by finding some pattern from the power sum and then use like the Pascal's triangle and binomial expansion. So that it was a great summary of what you do in the topic 1, isn't it? And for the topic 2, we saw interesting function of a sin x over x and its behavior with the graph, which is really the main thing that we do in topic 2, right? We get to see all the behavioral function, not only the algebraic part, but also behavior with the graph. Graphing is very important in topic 2, isn't it? And some transformation, right? And then we derive some series about the sin x over x, and we play around with it with the logarithmic function because it beautifully converts the product into the series. That's great. And in topic 3, what we saw is the great role of a trigonometric function to bridge between the real and complex, right? We saw not only the trigonometric function definition with the complex number, we used the complex number to define something called a hyperbolic function. And then we converted back and forth by substituting something with the ix. That was a great observation. And from there, we actually ended up making the power series for who? Cotangent x, hyperbolic cotangent, and then cotangent x. And that was what the end of the topic 3 was. And for the topic 5, we came back to the topic 2 and used the power function, power series of a ln of a sine x, and used the derivative to derive the power series of a cotangent x. And for that, we actually had to use something extra. What didn't we? We had to use the double summation. So entire series, we use only 2 extensions. The first one was Cauchy product. Second one was the double summation. But obviously, if you're interested in, you can study further. It's not that difficult at all. I just didn't want to explain further because it would lengthen the video. I just wanted to solely focus on things we learn, things we do learn in the syllabus. And then making the comparison with the cotangent function for the coefficient of x of 2k minus 1, we actually derive again this beautiful result of what? The zeta function with who? Bernoulli number. Only for the even. Okay? Obviously, you can discuss further for the zeta 4, zeta 6, or what about the odd, zeta 1, zeta 3, zeta 5, a pairs number. Yes, that's what we did. And that's why this question is so beautiful, because it really summarizes, it captures everything you do in AA, everything, everywhere, all at once. Okay? But that's pretty much it for this one. Let's briefly talk about the extension that you can make with the Bernoulli number for the probability, for the statistics. Just very shortly. Okay? That's it for me today. See you around. Hello, so topic 4 is about, the probability and statistics, talking about the chances, right? This is another scene from the Everything Everywhere All at Once with the sausage fingers, and if you're interested in why she has the sausage fingers, who knows? That's the statistical inevitability. Okay, anyways, let's get to the next part here. So Bernoulli number and probability, what is it talking about? Okay, so for that, I want to present you another very popular topic for the IA, which is a very, very nice one. It's the Stirling's approximation for the n factorial, right? If n is a very large number, this expression approximates the n factorial. And for the very large number, if you send n to infinity, their asymptotic behavior will converge to 1, meaning their ratio, in fact, will become 1. Okay? So that is a very, very popular idea, and you can actually choose it for your IA topic if you're interested in it. Very, very nice to associate with something called a gamma function. And in fact, it can be used with the Bernoulli number. Very interesting, very interesting. So let's have a look. So, what I want you to notice is this, those are the Bernoulli numbers, starting from the B0, B1, B2, etc. So if you look at the behavior, my friend, if you look at the size of it, just the absolute value of it, is it getting bigger or getting smaller up to here? It looks like it's getting smaller, right? Look at this, you got 5 over 666. It looks like it's getting smaller. But in fact, if you actually proceed further, it's actually getting bigger and bigger, right? Some part it got smaller, some part it got bigger. And I don't know whether it's going to be actually bigger or smaller. Well, we established already without proof that the odd term eventually, all 0 except for the first one, except for the B1. But what we want to do is, if you look at the decimal, look at this. Obviously it's getting smaller, but they got bigger again, right? Up and down, up and down. Would it be alternating? Would it actually diverge? You can actually prove it too, right? Will this behavior last? In fact, in the proof of that, for very large number of Bernoulli number, you can actually see the asymptotic behavior with something with the Stirling's formula, okay? So that's very interesting too. You can actually study for the IA again for your extended essay. And then on top of that, not only talking about the Bernoulli number with the Stirling's formula, you can also associate with the Stirling's formula with many probability distribution functions that you learn only in AI, unfortunately. It used to be covered in a higher level, but then it got separated. But, even for AA students, it's a great distribution great distributions to study, such as the Poisson distribution or the central limit theorem with the normal distribution. So those distributions involved with the strings formula, and you can definitely study for it. Okay, it's very, very nice. And on top of that, you can also associate with the Bernoulli number. And then that's why I wanted to end this video with this nice introduction of Bernoulli number that we thought that was hugely algebraic, that therefore involving with the topic 1, 2, 3, and 5, can actually reach some topics in topic 4 as well. And that's why I love this number with this expression, because this really, really summarizes everything we learned in AA syllabus. Hence, the question is called who? Everything, everywhere, AA once. Okay, but yeah, that's really the finale of this series here. That's really it for me today. I will continue to make the interesting video. So I made this question correlated to the movie called Everything Everywhere AA Once. But you know, who is gonna be jealous if we don't make AI, isn't it? And for the AI, I have a very good idea with the movie that I like to make. The hint clue here is Matrix. Oh, sorry, trilogy. Oh, okay. Spill the milk. It's going to be something with the trilogy, so please bear in mind, and I'm going to come up with that idea as soon as possible. Okay? But yeah, that's pretty much it for me today. See you next time. Enjoy!